So I was saying Professor Ginestra Bianconi from Queen Mary University of London and Alan Turing Fellow at the Alan Turing Institute. Her work frames in the area of complex systems and span a number of topics from complex network to multiplex networks, to cite a few. And today she's going to give us a seminar entitled Topology Shapes Dynamics of Higher Order Networks. So it's Ginestra, quickly to start.
Thank you so much for the invitation. It's a real pleasure to be here. Let me just share the screen a moment.
Great.
So this is about work that I've been starting in my group from 2020, and is about the interplaying between topology and dynamics. So this field is really changing, according to us, the understanding of complex systems. And complex systems are undoubtedly among the most challenging system for mathematicians, physicists, and computer scientists, because they give rise to phenomena that are notoriously difficult to understand, model, and predict. But what is a complex system? And you can answer by example. And for instance, the brain, through its billion of connection, give rise to the emergent property that is cognition. That is, of course, one of the big scientific challenge for the scientific community. Then we have the cell itself, that through the interaction between its constituent give rise to life itself. And then we have also physical system like the climate, or and also man-made system like the economy, which give rise to emergent phenomena. And actually, you can spend your entire life focusing on each of these problems. Yet from the mathematical perspective, one would like to understand what is common between these different systems. And so one can ask the question, is there a mathematical definition of complex system? And soon realize that, well, maybe one should give up mathematical. I mean, already defining what is the problem is already quite challenging, and we are not yet at that stage to define mathematically a complex system. But we have in 2001 the Nobel Prize awarded for research in complex system. So we gather together with the editorial board of a new journal, the JPhys Complexity, to reflect on the perspective of the field. And I really recommend you to read this work, because every editor has highlighted his own point of view for the problem, for the open problem for the community. And yet from this different perspective, it emerged some general consensus, at least among this group of editors. And it emerged that complex systems are, of course, interacting systems. Interaction are fundamental, that they encode non-trivial topology in the wiring of their interaction, that is typically encoded by networks. They have typically a non-linear dynamics, and actually they encode information. So all this interplay between topology and dynamics should be seen under the light of information theory and information processing. So this talk is about how this picture changes when we go from pairwise to higher order interaction. So networks are, of course, very important. If you consider, for instance, this ego-centered network, this node in the middle, and its connection, and the interaction between this connection, this can encode already a lot of information in the system that this network represents. And this is the basic yet very powerful idea under network theory, that actually the structure of the network encoded for the function of the system. But it has been soon realized that this picture is actually only partial, because, for instance, if this network represents a collaboration network, you might know the collaborator of the node in the middle, but you might not know, you might miss the teams, who is working with whom in which project. And this is encoded in a higher order network or simplicial complex that is not only formed by node and links, but also by triangle, tetrahedra, and so on. And this topic of higher order network is really flourishing, and there is a lot of research right now on this topic. And of course, one example, as I already mentioned, is a collaboration network, where you can have, for instance, 2 or more authors, in this case 3, collaborating on a given paper, forming a team. You know, higher order networks are very frequent in social system when you have group of individuals. But it has been becoming important to understand also higher order network is an important framework to understand also the brain, where higher order interaction have been proposed to capture the dynamics at different scale. So, for instance, at the scale of brain region, you can distinguish between 3 regions of the brain that are correlated pairwise, giving rise to a unfilled triangle, or 3 regions of the brain correlated having a higher order interaction. So, for instance, activating together, and this gives rise to a filled triangle, a higher order interaction. And you have also other type of higher order interaction, and I will speak about this. So these are triadic interaction, in which you can have one node regulating the interaction between other 2 nodes. And this occurs in a number of systems, including ecological system, and in the brain encode for the interaction between neurons and glia. So you can have 2 neurons interacting through a synaptic connection, and the glia practically interacting and modulating the current of neurotransmitters, essentially. So it's a node regulating an edge. So simplicial complex are a beautiful example of higher order interaction, and they're though formed not only by node and links, but also by the triangle, tetrahedra, and so on. And they are important because in their topology, they encode this higher order interaction that we have seen they occur in real system, but also they allow for a topological and geometrical interpretation of this higher order interaction. And this opens a completely new framework to characterize the interplay between structure and dynamics. So the interplay between structure and dynamics in network has been dominated by the important observation that combinatorial and statistical properties are key to characterize this interplay. So, for instance, we know that the easy model is always ferromagnetic on a network, or else, even more importantly, maybe for application, is that the epidemic spreading as a zero epidemic threshold on scale-free network, and though thanks to the scale-free structure of the airport network, the system globally now on the Earth is very fragile for the emergence of pandemics. But actually, the degree distribution or combinatorial and statistical property are only one part of the story, because if you look at higher order network, you see that also simplicial topology and simplicial geometry are fundamental to characterize this interplay between structure and dynamics. And this talk is about how topology affects dynamics. And I have wrote an introductory book by Cambridge University Press, providing the important element to understand this emerging new field. So we will study how topology affects dynamics, and we will study this on data, real data, but also on models. And over the year, we have developed different examples of models, a model of emergent hyperbolic geometry, and maximum entropy configuration model for simplicial complex. So we have a variety of systems with a control statistical, geometrical, and topological property that we can use to study the dynamics. With this background, we can really address a new complexity challenge, and this will be to practically combine topology, higher order interaction, and nonlinear dynamics in a non-trivial way to understand complex systems, including possibly the brain, the climate, but also AI algorithm. And possibly this new framework will be interpretable with information theory idea. So in this talk, we will supposedly mention about the interaction between topology, higher order interaction, nonlinear dynamics. Maybe in the next talk, we will deal with also information theory. So what is topology? Topology is the study of shape and their invariant. So for instance, a point is characterized by Betti numbers, and the Betti 0 is the number of connected components. Betti 1 is the number of holes, like the one that is present in a circle, a one-dimensional hole, and the sphere as a two-dimensional hole, so as a Betti 2 equal to 1. And if you look at a network, and also real network, you see that this cycle and this hole are very significant, and actually you can use topology to characterize the structure of this network using persistent homology, for instance, or applied topology technique. But this talk is about using topology to study dynamics. And actually, you can have dynamics of what we call topological signal. So you can associate a dynamics not only to each node of the network, but also to each edge, for instance, characterizing a current, or also eventually to each triangle, tetrahedra, and so on. So actually, this allows us to go behind the node-centered point of view of the dynamics of a network, and to attribute to a simplicial complex a dynamical state that is encoded by what we call a topological spinor, that is associated to a zero cochain, so function defined on each node, a one cochain, so function defined on each edge, and a two cochain, for instance, defined on each triangle, and so on. You can generalize this. And there are evidence that these topological signals are really present in complex systems, So we already spoke about synaptic signals between two neurons. Olaf spawns and also propose edge signal at the level of a brain region and a way to assess them. So you can have things associated also to higher order simplices. For instance, you can have a citation associated to a team, right? Three author, the citation that three author got in the paper they wrote together. Or you can have also what are called vector field. So for instance, a speed of wind at given location or current at given location in the ocean. These are vectors located at different point on a tessellation of the surface of the Earth. And then you can project this vector on the edges and then treat it as cochain, so function defined on the edges of your triangulation. So mathematical
question, sorry, Ginestra. So if I think about this framework also from like what we know from epidemic models on networks, there your mean field is like a node-based thing, and then you can go second order mean field where you consider pairs and triples and triangles. Is that similar to what you're doing here, or is this? Because there you have a sort of second order mean field theory where you sort of close at the second order because the node expectation values depend on the pairs, and then the pairs depends on the triples, and the triples.
I think this is in spirit of what Olaf Sports does with edge signal, but is way to define edge signal between two regions of the brain is the instantaneous correlation. Okay, so if you have some, if you don't do an average over a long time and you have something, a state of a pair of nodes that is instantaneous. Yes, and I think this is what you do in the epidemic spreading as well, right? So as long as you have a function of time and not a constant that is assessed.
Well, the dynamics of the hyper edges, for instance, can depend on the edges and the node states as well. It's not decoupled.
Yes, we will see that. So we will see that. Of course, we have not applied to this, so this is a good thing to think about this term about epidemic spreading. I will tell you what we have done, but of course, this is an important avenue probably to look at what is known about epidemic spreading in this slide. Yeah.
Thanks.
So you have a function defined on each node, on each edge or link, or in each triangle. And this defines your dynamical state of the simplicial complex. And then you can define operator, that, for instance, act on function on the node and produce function on the edge. And one of these operators is the co-boundary operator, or also the gradient. So the gradient does the difference between the function of the two end node and attributed this to an edge. So you can have the adjoint, so you can have a function defined on the edge, and you do flux in minus flux out, and this is the divergence, and you associate it to the node. Or you can also do the curl. So if you have a triangle, you can consider the circuitation of the current along the edges of the triangle, and this you can attribute to the triangle itself, and this is the curl. So there is this stereo calculus that you can associate it to this cochain, and this is encoded in what are called boundary operators. So these are rectangular matrices between node and edges and triangle. And it's a little modification respect to what people are used. They used to encode a network in an adjacency matrix that is square. These are a set of rectangular matrices, but it's not so much more complicated. And the B1 describes the discrete divergence, B1 transposes the discrete gradient, and B2 transposes the discrete curl. So these are the coefficient in front of the transformation which I show you. So for instance, for the gradient, you do the gradient of 1, 2 is 2 minus 1. So these are the coefficient in front of the linear transformation, which I showed you before. And they have an important property is that the boundary of the boundary is null. And this is very important in topology. So here I have a crash course in topology, but there is a lot of idea behind of this construction. So from boundary operator, you can construct Hodge Laplacian, and Hodge Laplacian are finally square matrices. So you can have B1, B1 transpose, or B2 transpose B2. And the Hodge Laplacian describe diffusion from n simplices to n simplices, like the graph Laplacian describe diffusion from node to node through links. The Hodge Laplacian describe diffusion from, for instance, links to links, going through node or going to triangle. And importantly, the dimension of the kernel is then Betti number. So there is an important connection with topology. And the graph Laplacian is well known. I think it's important building block of network theory, and it's described diffusion from node to node. And one important property is that the harmonic eigenvector is localized on the connected, is delocalized on the connected component. So it's constant on the connected component. So you will have one eigenvector on the yellow component and one eigenvector on the blue component. And these eigenvectors are associated to 0 eigenvalue, and they are constant on this component. So when you look at the higher order Laplacian, the harmonic component, you look at this left picture, are localized along the holes. You know, like the harmonic component in the graph are on the connected component, localized, so defined on the connected component. So that corresponding to the Betti 0. If you look at the one Laplacian is the eigenvector, the harmonic eigenvector are localized along holes, one-dimensional holes. So you will have one cycle, the other cycle. Of course, these are degenerate, so you need to choose the basis in a smart way. It might not be so trivial, but there is a basis that does that. And then another property is Hodge decomposition, meaning, for instance, if you have a function defined on the edges, there is a unique way to decompose it into a gradient flow, so going from a source or going through a sink, an harmonic component going along the holes, and a solitonial component, which is going around filled triangle, for instance. So let me just move to dynamics. I see I'm a little bit slow today, but hopefully it's nicer because I express more the concept. But let me go to the things, the research things. So one thing we apply this framework is on the Kuramoto model. The Kuramoto model is an important model to describe synchronization occurring in complex system. And the complex system is encoded in a network. Typically in the traditional Kuramoto model, the dynamics is defined on the nodes only, and is a phase that is oscillating with a constant frequency, but then phases of node that are connected by link are coupled together in such a way that they tend to be aligned. And then this term that couples them together as coupling constant sigma, and if sigma is greater than a certain threshold value, you have that a finite fraction of the phases oscillate together. And this is the order parameter of the synchronization. And this synchronization is a stylized model that can be used for a number of things, including at the coarse grain level brain dynamics, but also many other things, also in condensed matter, I don't know, coupled Josephson junction, or a large variety of systems. So in 2020, together with Ana Millán and Joaquin Torres, we ask ourselves the important question: what happens if the phases are, instead of being on the nodes, are on the edges? And so first of all, we realized that the standard Kuramoto model can be written in terms of the boundary operator. So practically, the node signal are coupled together if they are sharing an edge. And this coupling is nonlinear with the sign function, but if you linearize, this is a zero Laplacian. And having realized that, is immediate to show what is the dynamics for higher order Laplacian. So you couple links to links if they share a triangle or if they share a node. And here the linearized dynamics is given by the one node Laplacian. And interesting, this dynamics is a gradient flow of an Hamiltonian, and is well known that the Hamiltonian of the standard Kuramoto model is related to the XY model, which is a very important model in statistical mechanics. And now with this topological Kuramoto model, this is a gradient flow of a generalized Hamiltonian. So it's quite interesting feature. And another thing that we observe is that we can project on different modes of the boundary operator of the Hodge Laplacian. And if we project the dynamics on the harmonic eigenmode, since technically there is this property that the boundary of the boundary is null, all the interaction doesn't affect the motion of the harmonic eigenmode. So the harmonic eigenmode is free to oscillate and is not affected by the coupling constant, okay? So the free dynamics is localized on the harmonic mode, which are on the holes. So if all the other modes freeze, which is an assumption we can make and then we can try to validate, then what is left is only the dynamics on the holes. And here it's these two octagon, and you see this is when sigma is very high, so we can assume the other modes are freeze, and the dynamics is in either one of the two holes or in a superposition of the two holes, because this Hamiltonian has many minima. It's not just that there is one minima, like in a standard Kuramoto model where everybody does the same. As long as the network is connected, there is only one minima. Here there are two minima because there are two holes. And then the free dynamics can oscillate between this hole. And ideal, my dream is whether one can control where this free dynamics is and where this localization of one hole and the other load can encode information. So for instance, if this would be a good model for the brain, you would want to see if one hole can represent kind of one attractor, like one memory or something like that. But this is just my dream. So if you have one hole field, we recently realized that actually there is a way to characterize that one hole is filled and the other is not. So there are some order parameters that are sensible to this. And if you fill both octagon, there is no dynamics. So the dynamics is there only if there are holes. And having studying this, we can also study what happens to the other mode And in order to study what happens to the other mode, we can project the dynamics on the edge, either on triangles or on node. And these are the corresponding to the irrotational and solidonial mode of the dynamics. And we can study the dynamics of these two projected signal. And this is a decoupled dynamics. And we can see that these dynamics actually really freeze. So as sigma increases, this irrotational and solidonial mode really freeze, and then the order parameter is finite. And what is left is the free dynamics on the holes. And this occurs at zero coupling, but we can have an adaptive version of the model in which the coupling of edges, coupling together when they share a triangle, for instance, is modulated by the order parameter of the projected dynamics on the node and vice versa. And in this case, the two coupled projected dynamics are not the two projected dynamics are coupled by this global order parameter, and the transition becomes discontinuous. And this we check that it becomes discontinuous on this configuration model of simplicial complex. We check also on this network geometry with flavor, and we check also on data. And these are data coming from real connectome of Homo sapiens and C. elegans, and we find numerical evidence for this behavior. Actually, I didn't mention, but we have also analytical result on random graph and on fully connected graph showing that this is indeed a discontinuous transition. So this is so the topology, the dynamics learn the topology in this way because the dynamics go and sit on the holes of the structure. But actually, if you have a larger structure and one hole localized there, the synchronized dynamics will localize on the hole. So it will not involve all the edges of your simplicial complex because we'll sit there, right? So this is very different from the Kuramoto on the nodes because the Kuramoto on the nodes has a free dynamics that is constant over all the nodes of the network. And then we can ask ourselves, is there possible that this, for instance, this topological synchronization, for instance, this edge dynamics is global? It gives rise to a synchronization that is global. Can we have global topological synchronization? This is work with Timoteo Carletti, Lorenzo Giambagli, and recently my student Runye Wang and Riccardo Mulo. So in order to study global synchronization instead of having the Kuramoto model, which is more suitable for partial synchronization, we can use a couple identical oscillator dynamics. So we have a dynamics defined on the edges, for instance, or any simplicial d-dimensional simplices, and each simplex has a dynamics that is the same. It might be chaotic or very complex, but it's the same dynamic. So, but the initial condition might be different, right? And then the simplices are connected together by the Hodge Laplacian. On the graph, people use the graph Laplacian, but for topological signal, we need to use the Hodge Laplacian. And the thing is that the scenario is similar to what happens for the Kuramoto model. So if you have edge signal, this global synchronization can occur only on the holes, right? But or only on aligned to the harmonic component of the Laplacian. But while on a network, the harmonic component of the Laplacian is delocalized on every node of the network. So you always have a global synchronized state. It might not be stable, but it always exists. When you look at topological signals, since the holes might be here or there, you don't have this global synchronized state in general. You can have it only for some topology. And this topology, you know, they must have an harmonic eigenvector that is delocalized, constant on every simplices. And this is not always occurs only in special situation. For instance, if you look at the links on a triangulation of a sphere, or if you look at the links on a triangulation of a torus, then this will work, because roughly speaking, you have a hole that span all the links and all the triangles of this object. And really, in this case, you can have global topological synchronization, for instance, for the square tessellation of the torus, but this is rare. So on the torus, you can have global synchronization of each node, each link, or each square. And this is also for I-dimensional torus. You can have global synchronization of every d-dimensional signal. But this doesn't occur in general. These are very special structures in which this can occur. Okay, so topology dynamics learn what is topology. Can we have topological signals of different dimensions interacting together? So until now, we have seen only edge signals synchronizing together, partially or locally, or triangle signal. But can different signals interact together? And in order to do this, we need to use the Dirac operator. And the Dirac operator is inspired by Dirac equation. And Dirac wrote this equation in quantum mechanics in order to have a linear equation, so a linear operator, with a relativistic dispersion relation, so that if you iterate the operator twice, you get practically the Laplacian and plus a constant term. So the Dirac operator for simplicial complex defined on node, edge, and triangle can be defined in terms of the boundary operator in this way. And so it acts on this topological spinor defined on node, edge, and triangle. And what it does is allow crosstalk of the different topological signal of different dimensions. So because practically the signal on the nodes, you do the divergence and you put on the links. The signal on the links, you do the gradient and the signal on the node, you do the gradient and you put it on the links. You signal on the links, you do the divergence and you put it on the node, and so on. So it allows then the different topological signal to interact together. And this is very important for us, because the Hodge Laplacian only couple node and node, link and link, triangle and triangle, and so on. And interestingly, the Dirac operator can be interpreted as the square root of the Laplacian. So if you do the square of the Dirac operator, you get what is called the Gauss-Bonnet Laplacian, which is a matrix having the Hodge Laplacian in the diagonal. And the Dirac operator is quite nice, and it can have a wide variety of application. And for instance, let me mention the application in complexity. So of course, we would like to have a synchronization that now couples node and link signal together in a non-trivial way. And so here we formulate a synchronization, Dirac synchronization model in which you have a function defined on the node, a function defined on the edge, and a dynamics for the topological signal itself that depends on the Dirac and the Dirac square. And I don't want to go into the detail about this because we have very little time. But what happens is that the dynamics of node and links is now entangled. So the order parameter depends on a linear combination of node and links dynamics. And the synchronization is discontinuous. And this is even better than the discontinuous transition we saw before, because the discontinuous transition we saw before doesn't have a stable hysteresis loop, while this has it on random and fully connected network. And so, and when you change the order, this parameter Z here, that is a parameter of the model, the transition can go between two discontinuous transition to one discontinuous and one continuous transition in the along the hysteresis loop. So you ramp up sigma and you see one transition, and then you slow down sigma and you see the other transition. And we have a good theoretical understanding with some approximation. So this is the theory, and these are the simulation for random graph and fully connected network. And this also in this case, the harmonic mode is the free mode that remains, but this is highly degenerate, right? Because you can have many cycles in your network. So in general, let's say in this fungi network, you might have a dynamics that is highly non-trivial, and that we are only scratching the iceberg, because I think understanding the complexity of a dynamics of this sort could take us quite busy for many years. So I want also to speak about using the Dirac operator for practically partial differential equations. So finding, characterizing Turing pattern on networks. So, so Turing patterns are known to occur in the continuous, and on networks have been studied when the function is defined only on the nodes. But here we define a function or species defined on nodes and edges. And actually, we have addressed the question if we have two species on the nodes and one species on the edge. So because it is a well-known result in dynamical system that you can have a dynamical Turing pattern only if you have at least 3 species. So in order to do that, we need to have a 3-way Dirac operator now acting on 2 node signal and 1 edge signal. And so we have practically the boundary operator and the transpose, but actually you do the gradient of the node signal and you put it on the edges, but you have 2 node signals. So you go from 1 node signal to 2 node signal, and then you have an edge signal and you do the diversion, and so you go from 1 edge signal to 1 node signal. So this matrix delta is like the Dirac operator, but it's not square anymore. So in order to project back on the topological spinor, we need to introduce some gamma matrices, and these gamma matrices will reshape the projected dynamics. So you have a node signal that is 2-dimensional, you project on the edge, it becomes 2-dimensional, and then you reshape it to make it 1-dimensional. And then you have one function on the edges, you project on the node, is 1-dimensional, and then the gamma matrix will reshape it and make it 2-dimensional. So you have this slash that is the multiplication between gamma and delta, and you can study the emergence of Turing pattern. And interesting, we find that the Turing pattern driven by the Laplacian, the Gauss-Bonnet Laplacian, are diffusive-like and quite interesting. but the Dirac pattern have very non-trivial property that are already visible through this movie, and we are investigating whether this is also depending on one of the symmetry of the Dirac operator, which is the chirality. So we also study the Dirac operator to do signal processing. So you can have function defined on nodes, edge, and triangle, and this can be data, right? So for now we have seen that the dynamics learn the topology, but actually also we can have a dynamics and we can use topology to process data. So we have data defined on node, edge, and triangle, and this is the true signal. And then we have actually access only to the noisy signal, where this signal have an addition of a noise. And a question would be, can we reconstruct the true signal? And the question that we ask ourselves is, can we do that jointly by considering node, edge, and triangle signal jointly? And this is work with Lucille Calmon and Michael Schaub. So what we did is that we consider, so you have the true signal S, you add the noise, and you have the measured sigma as signal S tilde. And then the question is to reconstruct in such a way that the reconstructed signal is close to the measured one with the L2 norm. And then we have a regularization term. And this regularization term is such that if this parameter M is 0, we have this square. So we have a Hodge Laplacian kernel or Gas-Bonnet Laplacian kernel, which treats signal of node, links, and triangles separately. So it's not what we want to do, and it has been already quite extensively studied in the literature. But if M is different from 0, then we have something that really couples signal of different dimension. So, you know, in terms of the eigenvalue of the Dirac operator, the Hodge regularization term is just a parabola with 0 at 0. But what we have is actually this, this parabola shifted so that practically you don't filter the eigenmode corresponding to the eigenvalue M. So you practically keep that mode, and this mode might not be the harmonic one. And then there was another kernel we originally studied, but is performing worst. So now practically we have this kernel which filters out the signal if they are going away from M, from the eigenmode M. But M is not a parameter, but we can also interpret M as the expectation of the true signal on the Dirac operator. And actually, we can learn M. So if the signal has one dominating eigenmode of the Dirac operator, we can learn the value of this eigenmode, and so we can filter out all the other modes, and we keep the most important one. So here we first look at a sample network, the Florentine family. We took a true signal aligned to an eigenvector of the Dirac operator, and then we swap we slice M. Now M is not learned, but so as a function of M, we see that the error in which we reconstructed the signal can have a very significant dip. So we can improve respect to the orange line, which is the Hodge Laplacian signal processing, quite a bit. But M can be learned, And actually, we can have an algorithm that if the noise is not too big, can learn M, and as we iterate this model, really we can approximate M with a true one, and the error accordingly can go down. And we apply this to this network geometry with flavor, finding good results. And we apply this on real data of buoy in the shore of Madagascar, and finding good improvement with respect to the Hodge Laplacian. But we have also now working on some extension, and we have also a way to have much better improvement. Sorry, I just want to ask, should I end here, or because I have several slides left, so.
Please go ahead. I would say.
I think there is still time.
We
So
are.
if you're ready,
We're still paying attention, so maybe. So I just wanted to ask a quick question also to satisfy my curiosity. So the Dirac operator. So M usually is at the mass of the fermion, and it's fermionic operator in. So.
Okay, so this M here is actually we choose wrongly the name, so we will change it in next. So this is more the energy of the Dirac than the mass. But there is a way to define the mass, yes.
And
this is the energy of a massless Dirac fermion in some sense. But
before you mentioned that the boundary operators are also nilpotent, so that also smells like fermions. Is there a relationship with supersymmetric theory or something in that lines that we have in TDA, the same link to supersymmetric?
Yeah, maybe we can discuss this when I come there. Yeah, so there is quite a bit of relation to so this Dirac operator, I work on it for several years, and finally maybe I track back the story of it. So it's very strictly related to a staggered fermion proposed by Kogut at Susskind in the 70s. But what they did is that they actually didn't say node and links. They say we double the nodes and we put another node in the middle of a link. So the relation was not strict, direct, but then people in non-commutative geometry have been using it, and yeah, so in complexity is certainly new, I think, but the story, of course, can be tracked back.
Nice, thanks.
I have one question.
I have a question.
When you said that about direct signal processing and about filtering signals, filtering direct signals in this topological structure, I don't know. When you talk about filtering and signal processing, we might be immediately about Fourier analysis, for example, the Fourier transform of a topological signal. Have you ever like thought about that, like define a analysis of?
No, that's certainly true. So if you have a lattice, the eigenvalue of the Dirac are connected to the Fourier. So the eigenmode are the Fourier component, and the eigenvalue are the eigenvalue of a lattice of phonons on a lattice. So it's but in general network, the corresponding of the Fourier mode are the eigenvalue of the Laplacian or of the Dirac, the eigenvector of the Dirac operator. So everything, also when we define, for instance, I define the mass of a network with a non-Boolean approach. Practically, what is there, the wave number in a network is the eigenvalue of the Dirac. So if you have a lattice, you have the wave number, but if and the Fourier mode. In a general network, you have the eigenvector of the Dirac. But this is well understood also in signal processing. There is this very famous paper by the people in the PFL and Bronstein that...
There is an emergent mathematical tool that calls topological signal processing, like I think a paper published last year by Sergio Barbarossa. And he also will go to a workshop in Delft here nearby. So it's very interesting subject to talk about this topological signal processing.
Yeah. Would love to speak when I'm
I have one question just because it's related to what you just speak before you move on. Is very interesting that the signal is concentrating the boundaries, and there is an analogy in condensed matter physics with edge states, where you have this topological protection in some topological insulators, where also everything stays in the boundary of material. I wonder if it's just an analogy, or if there is any relation, or what do you think about any relation between edge states in condensed matter physics and the edge signal that you found?
Yeah, I don't know. Yeah, I don't know. I think it's not strictly related, because if you have like a square, right? And like a square, a topology that is a square, I would say you have a Betty 1 equal to 0. So that the edge signal of, condensed matter is not the same edge that I speak about, but maybe I need to study this, because I think it's very interesting question, and maybe there is a connection. It's just that I don't see it now.
Thank you. Maybe when you come, we talk more about that then.
Yeah.
Thanks.
Yeah, sorry. Let me just, here we saw that dynamics learn where the topology ends. Topology can also be process dynamics. And then the next question is, can topology become dynamical itself? And this is a question we address with Anlin Sun, Filippo Radicchi, and Jürgen Kurs in a Nature Communication of 2023. And more recently with Anna Millan and Joaquin Torres. I hope to get there, and Anlin Sun. So triadic interaction, when one node affects the interaction between other two nodes, as we mentioned before, and this regulatory interaction can be positive or negative. So for instance, for ecosystem, you can have a third species that can enhance or inhibit the interaction between other two species, and so on. So this is another element which enriches the dynamics of higher order network, is the sign interaction. So we study this triadic interaction in the framework of percolation. So percolation, you assume you have a network, and you assume that the fraction P of links is damaged, 1 minus P of links is damaged, and then you monitor the size, the number of nodes in the largest connected component, which in the thermodynamic limit is the giant one. And you study this. So as a function of P, you study R, the fraction of node in the giant component. So in a random graph, this leads to a famous second order transition. So if you go from right to left, as you damage, the fraction of node in the giant component goes down, and then goes to 0 if the network is infinite in the random graph. And then for P less than PC, you have only infinitesimal component. And this is captured by these two very well-known equations. So in percolation, typically you damage and then you see what happens and you monitor what happens. And this is very important for robustness of the system. But in many situations, you don't see that. So you don't see a static response to a damage, but you see rather a giant component that evolve in time. And this occurs, for instance, in the brain. If you look at a movie of resting activity in the brain, you see a giant component that change dynamically in time. And in climate network also, you have a giant component that change in time. So the question is, can percolation be turned into a fully fledged dynamical process? And so we consider this network with triadic interaction. So you have practically two networks or a duplex network in which you have node, yellow node, cyan node, and links, structural links, these black links, which we are also indicated by a diamond. And then some of the nodes can regulate up on down, or up on positively or negatively the edges. And these are the regulatory interaction that can be positive or negative. So the question, the idea is to have a model of percolation in which regulator node determines which link are active and structural interaction determine which node are active. So there is a two-step process. Step one, you evaluate the node in the giant component. The nodes that are in the giant component are active. And in step two, you regulate the edge. So there is a rule, a Boolean rule to regulate the edge. Of course, you can choose any rule you want. We choose one that we can treat it analytically. So this rule is we deactivate all the links that are connected at least to one active negative regulator node and are not connected to any active positive regulator node. And all the other links, so this is a deterministic Boolean rule, and all the other links are damaged with probability 1 minus b. And then we repeat from 1. So we have a network, all the nodes are active, this node is active, but is a negative regulator of this edge. So at step 2, this edge is removed, and this as well is removed. And so since these two edges are cut down, so these two nodes are not belonging to the giant component anymore. And since this is damaged, this is a positive regulator of this edge. At the step 2, this edge is regulated down, and so on. And from this toy model, you see that at time 2, you find the same exact configuration that you have at time 4. So this is something new, and so we call it blinking. So it's a configuration that repeats itself. And this is captured by our theory, which is just the two equations for percolation plus another equation for regulation. And these three equations can be considered as a map. So if you have the fraction of nodes that are intact, the fraction of edges that are intact, you calculated the node in the giant component. If you know the probability the node is in the giant component, you calculate the probability that the links are intact. And this is a map. And so you can go and have a period 2, and these are the simulation corresponding to that. So the fraction of node in the giant component can oscillate between 90% and 50% in a periodic way. So this is a kind of simulation for this. So you have a blinking, so a giant component oscillating between two configurations with different fraction of node in the giant component. But of course, you don't have only blinking, but you can have a full root to cause. So the fraction of node in the giant component can undergo a root to cause. And this is captured by our theory. And then we have really that the fraction of node in the giant component can change in a chaotic way, of course, in the infinite network limit. In a finite network limit, you have a finite number of states, but in the infinite network limit, this is the dynamic. And this map is in the universality class of the logistic map. We check that analytically. And what happens is that the phase transition, so when you change the fraction of node as a function of the probability that the link is intact, in absence of triadic interaction, it is a second order transition. But in presence of triadic interaction is a full orbit diagram. So you have a theoretical prediction with a discontinuity, a period 2, a period 4, very rich diagram. And this is the prediction, and the Monte Carlo simulation is impressively similar, taking into account that the theoretical prediction is mean field and deterministic, while the simulation are with a lot of order parameter and are stochastic. So this is, we check on random network, for instance, in configuration model of network with given degree distribution, but we check that also on real network topology. So we don't want to be realistic, but we want to just to check that if the topology is not a random graph, the phenomena is also observed. So we took a mouse brain network with random regulatory interaction, and we see blinking, and we see chaos as well. So this is really nice. And when there are only positive regulation, this non-trivial dynamics is simplified, and you only have you still have an interesting phase diagram, but you only have a discontinuous hybrid transition. So we also check what happens if you don't have a step 2 dynamics, but you introduce some delay. So the regulation is not, the node is not regulating the link at the next step, but at tau step from it. And the dynamics still remains non-trivial, although it might not be in the logistic class universality, in the universality class of the logistic map. Finally, we study with Anna Millan and Joachim Torre and Lin Sun what happens if the network is spatial. This can be treated only numerically. So the interaction are only spatial and the regulation are only spatial. And in this case, not only the fraction of node in the giant component is non-trivial, but also the topology. So the shape of the giant component is non-trivial. So you can have cluster of activity, octopus or stripe, and we detect that visually. We perform a topological analysis with persistent diagram to characterize these different pattern. And then we, based on this topological persistent diagram, we did a classification of the dynamics. So we have a pattern and we classify either octopus, stripes, or cluster. And then we can study the dynamics of this pattern, because practically as time goes on, you can have stripes and octopus and cluster, and we can study the dynamics of this topology, changing topology, and we find intermittency. So it's a numerical work combining topology and showing that really the giant component is not only changing in the fraction of node in the giant component, but also in their topology. And this is some example of this pattern. So you see stripes, and then it turns into an octopus, if you're patient enough, yeah. And this is the opposite. You have an octopus that turn into stripes as time goes on. So let me just should turn into stripe at some point. Yeah, here is the stripe and so on. So really this triadic interaction makes the topology dynamical, and the giant component is changing chaotically in the fraction of node in the giant component undergoes a route to chaos, but also the topology of the giant component changes in time. So I reached my conclusion. Sorry, I was a little bit late. So I wanted to show you this interplay between higher order interaction, topology, and nonlinear dynamics. And I wanted to convey the interest in this interaction. So the one basic idea is that the dynamics of a simplicial complex is encoded in what we call a topological spinor, defined on node, edge, triangle, and higher order simplices. You can study dynamics at a given dimension. So for instance, synchronization at the edge level, but you can study also the dynamics of different dimensions together. And when you do that, the Dirac operator is really I think, key operator to capture this interaction. And then topology can become dynamical itself when you include a triadic interaction as the one observed in neuroscience and climate. So we hope that this theoretical idea will find a real case study in the future. So I want to thank all my collaborators, of course, people that have been in my group. At the current moment, I spoke only of the work of Rune Wong that is just starting in my group, but Anlin Sun and Lucille Camon have been my student in the past year. I spoke about their great research. And Anna Paula Millan has a history of being in Queen Mary, but also in Amsterdam, and also all my other collaborators. So thank you so much for your attention.
We still time for a few questions. Someone has?
Claudia first. Yeah. Maybe you can unmute and ask.
Yeah, I have some question on the when you talked about the Kuramoto model, you gave some example, and I did not really understand. So you implemented the dynamics on some real networks where you had where the networks came from. Like, how did you choose the high order? How to place the high order, to place the low order? How do you choose that?
Yeah. So, okay. So this is, again, not to be meant to be realistic again, is also an example of what happens if you have a realistic network. So these are freely accessible data set of connectome and not very big at the level of brain region. So what we did, this is our network, of course, so this node and links only. So what we did is what is typically done when you don't know if there are higher order interaction, but you want to include them. So we consider the clique complex. Of course, this is not meant to be something realistically realistic in any way, but it's just an idea that this doesn't happen only if the graph is random or according
you
to
had some measure on distances between the kind of correlation between three nodes or something like that, and then place the high order on these ones. No. Yeah, okay.
Yeah, you can do with distances. What we did is we did the clique complex. So the clique complex consists in whenever you have a triangle, you put a two simplex. Whenever you have a four clique, you put a tetrahedra. Of course, this is
okay, I see. So when you say whenever you had a triangle, you mean whenever you had a triangle in the pairwise network, then you put okay.
That's the clique complex construction, which is of course overestimating.
Yeah.
Even assuming that there are higher order interaction, the clique complex is overestimating what is the truth.
Mm-hmm.
But is a way that is standard in topology. So
yeah,
we went for that.
Yeah, and then I had two other questions in that context. I mean, I guess one is more general. You're working with the nodes, the edge, and the triangles, and you have defined your boundary operators. So this is in your first part of your talk. But I guess you can also define probably a boundary operators for high order, like with a plus minus. So right now you're working, all the things that you presented were stopped at triangles, right? But you can also generalize for high order.
Not really. So I didn't told you that, but I show you a picture here. So this is not triangle. Here we capture square. So you have cell complexes with generalized simplicial complexes. So you can have square regular polytope instead of simplices. So you can have.
But you don't go to
so
tetrahedron
you can have.
or higher dimensional tetrahedron.
Sorry.
You don't go to tetrahedrons.
You can go to, for instance, this construction with this cell complex. You can go with any hypercube. So yeah, I have several works on cell complex. So practically, it's quite interesting because in 2 dimensions, the cell can be whatever. And also here, when I show you this picture, this is this one. This is a cell complex. You have an octagon, right? So in the polygon can cell. In 3 dimensions, you have the platonic solid. So you have the icosahedron, the cube, all the platonic solid. In 5 dimensions, also you have so many, and actually some guys with a lot of phases, like 300, or they're really crazy. But if you go above 4 dimensions, there are only 3 types of regular polytopes. So you only have the simplices, so the fully connected kind of clique, and the hypercube, and you have the orthoplex. So practically, if you want to have some theory that generalizes to any dimension, you just work with these 3.
But slightly related to this, I guess that chain of co-boundary operators and boundary operators that can define, let's say, a cohomology going on beyond the triangles.
Yeah.
And then you get a higher dimensional Dirac operator that works.
Yeah.
Question, right? Yeah.
Just that to show the formula for general,
Yeah.
There is a general formula that is D plus D star. The Dirac operator is D plus D star, where D is the exterior derivative, but yeah, I think it is more intuitive if I show from node, links, and triangle. But of course, triangle can be in reality any polygon, and actually dimension D equal to 2 is not a restriction. You can go in any dimension. So you can go cell complex and you can go any dimension. This is.
But for finite graphs, it would stop at sort of like n simplices, where n is the number of nodes. But then you can also consider just the dynamics of the nodes in the exponentially large 2 to the n sort of configuration space. And do you know if there's a link, or if there's some work on the link between these kind of this cohomology picture that you paint here, and yeah, just dynamics on networks where you consider all possible colorings of the network, all possible configurations of nodes, or maybe this is just a far-fetched idea.
Yeah, all what I spoke about here is something, except for the triadic interaction, is something which the number of simplices doesn't change. So I don't consider, so I consider a given, I start with a given simplicial complex. So it can be arbitrary, but is a given state. So I don't consider ensemble of simplicial complexes, which would of course go in the direction of counting how many there are of a given property or something like that, or changing from one dimensionality to another. But with the practical, maybe with the with the triadic interaction, I do that because there it's the topology itself that is dynamical, and then we are actually exploring different topology. So there, the number of links change in time, and but the first part we start with something finite, and but yes, it's important.
I have one very last question, maybe more general. You presented today like more direct problem where you have a certain topology and then you study the dynamics on that topology where you define what type of dynamics you're looking at. I'm wondering if you, and then you look at properties. I'm wondering if you did the also inverse problem as well. If you ask the question of like what type of topology may have produced certain type of dynamics that you're observing. Yeah.
Yeah. So for this topological question, we have not addressed inverse model for the moment, but we have one worker recently, I think last week, for detecting inferring triadic interaction from data, and this triadic interaction in that model are only affecting node signal. And so we practically had a way, an information theory approach to kind of characterize when the triadic interaction are there. And yeah, we apply to gene expression data where there are also trigenic interaction are known to occur.
So this is on stationary data, or is it dynamical?
We have a model that is dynamical,
okay,
but then we apply to gene expression, which is in some sort of static.
Okay, thank you. Thanks a lot.
I have
one question, Fernando.
Yeah. First, thanks for the talk. It was really nice. So in a way, you leverage the nice mathematics of algebraic topology to network science, but there is some case where the simplicial structure is not valid. Like even in the co-authorship network, like in order to be a simplest, like 3 authors must publish together, and all the pairs must publish together, and you have to be single author as well. So it doesn't work all the time. Did you think about like making all this framework also for hypergraphs, or where is feasible, where is not feasible?
So we have a paper addressing this with Baccini et al. A few years back. And there the point was a little bit different. Of course, yes, you can go for hypergraph, but then with hypergraph you lose a little bit of topology. But actually what we claim is that if you have an hypergraph data set, you can always encode it in a simplicial complex without losing information, as long as the simplicial complex is weighted. So if you choose the weights of the edges in a certain way, you might encode in the weight the presence or not of a simplex in your data. So you might transform hypergraph data into simplicial complex data without losing information. So practically, the idea is that if you have a triangle but you don't have the links, right? And you have, one paper between 3 authors, you associate to the links 1, because the triangles they belong to have a 1, right? You associate to the links the sum of the weighted of the triangle incident to that link, right? But then if a real paper is between 2 of these authors of the triangle, you add to that number another number. Like if they have 2 papers together and they just pairwise, and one paper, three people, the weight of the link is 2 plus 1. And then when you do this, the transformation is linear, so it's invertible. So if you look at the weighted simplicial complex, actually you can invert the transformation and get the full information about the hypergraph, including which hyperedge are really there and which are not.
Nice. Can you say again the reference? Sorry, because I want to read it.
Yes, yeah, I can put it on the chat maybe.
Thanks.
Maybe in the meantime, there's another question by Sarah.
Thank you. It was amazing talk. And I would like to go back to the original question posed by Fernando, which you mentioned regarding topologically insulated and edge dynamics. Word, is actually general for cell complexes. In fact, one of the slides that we just showed now, it's very, very, very akin to topological insulation. And since it's general, couldn't be linked to edge dynamics in connection.
Hello?
We can't hear you very well.
Oh, yeah. Sorry, can you hear me now?
Yes,
Now it's much better.
Oh, yeah, sorry. My microphone was tuned down. Sorry, first of all, it was amazing talk. And I would like to go back to the original question posed by Fernando regarding convex matter physics and topological insulators and edge dynamics. Given that your work is general for cell complexes, perhaps there is a mathematical link to really establish that link between what you've done here, but also with edge dynamics as observed in convex matter physics. So it's very tantalizing, the similarity. So, I mean, do you think that it's possible to establish that link, really? Because it's really akin. It's so
Yeah,
akin.
yeah, I hope so. Maybe I study before I come back to Amsterdam in June and we can discuss a bit more. Yeah, I meant to study a bit, but then I was driven away because I have other connection more to
Okay.
high energy that were keeping me busy. But yeah, that's certainly an important thing
That
to.
would be that would be very interesting because topological or edge dynamics generates robust dynamics and I mean very very interesting properties for complex systems, and I think it will be very relevant to go into that matter.
Yeah,
anyway,
yeah.
thank you so much for your talk. Amazing talk, really.
Thank you.
Thank you.
I think we can thank the speaker again, Ginestra again.
Thank you.